Okay, hello everyone. We have reached to the last chapter of our course. This is entitled Structure from Motion. Uh, we will try to finish this part in, I think, about five sessions. The first one will be devoted to, as indicated here, pose estimation. And then I'm going to talk about stereo parallel located cameras. How do we use those kind of imaging systems for our purposes? Then for a more general case to apply the obtaining structure from any position of cameras, multiple cameras, or a single camera moving in time, we have to talk about epipolar geometry, which is the algebraic formulation of the geometry that we have. And we will define E matrices and F matrices in two different sessions. We will talk about them, how do we use them. And finally, I'm talking about triangulation and bundle adjustment. Let's start with what we are doing right now. First of all, let me remind you or emphasize this is not the only way obtaining shape, 3D shape from images. You can extract 3D geometry from images in various ways. One of them we have already seen, okay, the photometric stereo. And photometric stereo is also a very similar technique called shape from shading, or one typical approaches that we can use images to extract 3D information. Although we are not dealing in this course, shape from texture, shape from focus or defocus, structured light are also other techniques, okay? Therefore, as you can see from here, texture has important clues about the 3D geometry of a scene or object. Similarly, by projecting some known structure using a light projector just like here, okay, and getting the image from a camera, we can find any 3D information easily with respect to the things that I'm gonna show you here. But the thing that I'm gonna talk today is more general, just visual data, nothing else. And there is no constraint about the scene that what we have to do. And it's a very popular and robust technique. Right now it is shape from multi-view or shape from motion is one of the most fundamental techniques to extract 3D information from visual data. Okay, now let's talk about what are the fundamental problems. Maybe the most important thing is where are the points that I observe in my image in the 3D world, the positions, the coordinates of the objects in the 3D world. This is the most fundamental thing that I have to answer. Another thing is we have multiple images, as I have said, either due to motion or multiple cameras. How do you find one point in the next frame with the corresponding 2D point? In general, we have already talked about these things in our feature extraction chapter, but to here, for parallel cameras, I'm going to focus a little bit on this topic as well. And finally, if you're talking about 3D extraction, you have to obtain the positions of the camera with respect to each other in the 3D world. Therefore, we call it camera projection matrices, as you remember. Those camera projection matrices depends on the orientations of the coordinate systems between cameras. Okay, these are the fundamental questions. The second question we will not consider that much, but the first one and the third one I'm gonna talk about a lot. Okay, now once again, reconstruction of the 3D scene and estimation of the camera poses from multiple images is one of the most important problems in visions, but also very useful for any practical engineering problem. In this chapter, I'm going to assume I know the correspondences, except for the stereo part. I assume that I have my shift features which are already matched to each other. They are available. And mostly I'm going to assume cameras are calibrated with the techniques that you have seen in homework 3 or in the lecture notes. Okay, now I'm going to basically go step by step. I'm going to solve 3 problems. Or examine 3 problems. One of them is pose estimation. Okay, the second one is stereo imaging. And then I'm going to talk about structure from motion, a general solution from multiple cameras. One interesting thing here is for pose estimation problem, I'm going to assume that's a little bit slightly different problem. I'm going to assume I have a known 3D structure in the scene, a model, a calibration pattern, any arbitrary object, but known 3D geometry. If it is available, I'm going to find my position of the camera with respect to this object, and I'm going to estimate the motion camera geometry. Okay? For this purpose, this is the first, this video's content. I'm gonna assume I have the 3D information with respect to a coordinate system of the object, the model, the CAD CAM, or the world coordinates, I don't know. And you have some pixels. I'm gonna assume I have these matches in between, okay? Automatically I obtain them or manually, I don't care. But having these 3D coordinates and 2D image pixel positions, I'm gonna try to solve the geometry. This is called pose estimation. That's a very important problem. The second problem I'm going to talk about will be stereo, 2 parallel cameras, exact copy of each other. This time, the motion, the camera relation, camera pose in between is known because they are parallel. We have the information baseline, their distances. And the only thing unknown is 3D structure. Now this time I'm going to have matches between left and right cameras. Therefore I'm going to have matches between 2D to 2D, and I'm going to find the 3D information in the scene. This is stereo imaging. And finally, I'm going to talk about something general, structure from motion, where this time, for example, 2 or more images are available, and I don't know the scene, geometry, 3D information. I don't know the poses, the locations of the cameras, views with respect to each other. The only thing I know will be their feature matches between frames. Again, as I said, I'm going to just go on these things one by one. I'm going to today start with this pose estimation. Okay, now I assume I have n 2D, 3D correspondences. Okay, and I'm gonna try to estimate the projection matrix. The projection matrix should give me the internal calibration maybe, okay, K, and rotation and the translation, the transformations between 2 coordinate systems. One coordinate system is with respect to the world coordinate system or object coordinate system, something easy to make measurements inside. The other coordinate system is your camera coordinate system, where the origin is here, okay? Therefore, my aim is finding the rotation and translation between, and maybe finding the internal calibration camera matrix, okay? And finally, obtaining the projection matrix. In the course, we usually call it P, but I call it M in the slide. Now, previously, in the past lectures, during calibration stage, okay, I already talked about this estimation of the projection matrix, okay? Now, let's assume I have the world coordinates, okay, like this, in P. It's in homogeneous coordinate system, okay? This is with respect to your CAD CAM drawings or whatever real world coordinates, and there's a 1 for homogeneous. And 3 by 4, these are row vectors, 1 by 4, 1 by 4, 1 by 4. And if you just multiply them, just this M matrix, 3 by 4, you will obtain nothing but your pixel coordinates in homogeneous. This is in, note that this is in P3, this is in P2. Okay, now if you just write these things in a different way, noting that in this pose estimation problem, I know 3D coordinates, I know pixel coordinates, therefore the only thing unknown is middle part. What I'm gonna do is, I'm gonna just write these three rows as a column. Please note M1 is 4 by 1, this is 4 by 1, this is 4 by 1. The whole thing is 12 by 1. There's a vector here, 12 by 1. And all these things are known to us, okay? 3D coordinates and their homogeneous pixel locations. And that's equal to 0. Therefore, I'm talking about here a problem like AX is equal to 0. And note that in practice, sorry for that. In practice, we don't know this is not exactly satisfied due to the errors or the noise in the data. Therefore, we have to solve it in a different way, or I call it Q of X. Okay, let's make it Q. Okay. Now, there are 12 equations. If you have 6 2D, 3D pairs, all of them gives 2 equations, and you will solve, have a solution for this M matrix. And as we did before, this is just nothing but this problem can be converted to minimization of this thing, okay, and with this constraint, okay, and we have already seen that at the end one can show that that is equal to nothing but the eigenvector of this is equal to the eigenvector of Q transpose Q. The minimum eigenvalue and the corresponding eigenvector is our X that we have. Okay, we did this before during our calibration part. I have shown a relatively heuristic method at that time, but I can say that decomposition of, note that I obtain this M. The first part is 3 by 3. This is 3 by 1. The last pawn is. Now this part is equal to K times R, okay, and this part is equal to K times T. Now please note, finding the M, the 12 parameters here through this solution, and then this 3 by 3 matrix can be decomposed into a upper triangular and orthonormal matrix using something called QR decomposition. Okay, QR decomposition is a well-known technique in linear algebra where you have one orthonormal matrix and one upper triangular matrix, and you can decompose it easily, which means after estimating M, obtaining K and obtaining R is also straightforward. Then through K, using this relation, you can obtain, taking the inverse, and you obtain nothing but T as well. Therefore, now we have shown a technique where we can find a minimum 6, but it could be larger, to obtain the corresponding poses for a given 3D model and the corresponding pixel locations, and we find their pose in between two coordinate systems. Now I'm going to show one other technique. Okay, this technique only requires 3 points. Okay, therefore with only 3 points I'm able to obtain my pose again. Previously at least 6, maybe more than 6. This is called P3P. It's a very old fundamental technique. I think it's 1841, the first proposed approaches related to these concepts. Now let's see, what do we have? Only 3 points. I know their distances here, okay? I know this distance, I know, sorry, this distance, and that distance, okay? And from these distances, I'm trying to find, knowing these pixel locations here, these distances here, I'm trying to obtain rotation and translation in between them using only 3 points, okay? If you know the intrinsic calibration, then we have a solution by Haralick, and also determining the depths, there is another solution by Fisher and Bowles based on Ransack, okay? And there are some other solutions. I'm going to explain shortly that in fact there is not a unique solution out of this equation, but you can use a fourth point to disambiguate the solutions and find the unique solution. Okay, there is a beautiful tutorial in CVPR 2015, and you can look at that one as well. Now, about this P3P, I'm going to try to explain it briefly, okay? I'm going to assume such a structure. There is a triangle, three-dimensional, A, B, C, and known to me. I know exactly their measurements. There is an unknown origin, unknown to me. This is my aim. This is the camera origin, in fact. These are the vectors that we obtain, okay, P1, P2, P3. These three vectors are giving us the ABC locations, okay, the ABC locations, and the ABC are known to us, but I don't know the P1, P2, P3 vectors because I don't know the origin. Okay, now assume there is an imaging system somewhere inside. I don't know it. I'm gonna try to determine, this is my problem. But I assume at this point, camera is calibrated using the techniques that we have seen in the lecture courses. Okay, now we have ABC, and the P1, P2, P3 are our vectors. These are vectors for us with an unknown origin, starting from an unknown origin. Obviously, the difference between these vectors' magnitude are given this ABC, the known three scalars. Now, this triangle is projected to an image with a focal length f and the optical center O, okay? And now let's assume I'm observing perspective projection, okay? The xi and zi, which are the coordinates of my this vectors p1, for example, p1 is equal to x1, y1, z1. UI and VI are the things that I observed in my image, okay? Therefore, this is QI known to me. There are 3 points on the image. Please note I'm talking about something like this. This is the triangle. There is an unknown thing. I'm just crossing them. This point, that point, that point. This is my triangle on the image. I don't know anything about the coordinates here and this one. Therefore, I'm trying to obtain this information. This is my focal length of here, okay? Now, these are our, like, this is your U1, V1. This is your P1, for example, okay? Therefore, it goes on like this. Now, the J1, J2, J3 are the 3D unit vectors, okay? They are pointing the from the image. Therefore, I'm talking about this. This is your J1. This red one is your J1. This is, obviously, it is, I made it, this is maybe not unit, but I just divided here to make it unit vector. Therefore, this vector, in fact, that is equal to U1, V1, and F. This red vector is equal to U1, V1, and F. J1 is the unit vector corresponding to that. Now, let's consider this little trigonometric trick here. Please note between this blue one and this black one, P1, okay? Please note we have an angle. In between them we have an angle. Now, obviously, if we take the inner product between the unit vectors, these inner product between the unit vectors, that will give us those angles. There are three angles. We call it alpha, beta, gamma. And I know that I obtained the cosine of these angles by just taking the inner product between them. Okay. Now, a final thing, the relation between this J1 unit vector and P1, I assume there is an S scalar. J1 is unit, P1 is not unit. There is an S scalar, S1, which gives you the information between P1 vector, J1 vector, and S1 scalar. Okay, like a 3, 4, 5. I don't know. That's a thing that we don't know right now, but that's a scalar. This is a distance parameter. Now, again, these are unknown distance parameters. Let's try to write known A, B, C in terms of P1. The magnitude, square of the magnitude, you can write it P1 minus P2 transpose P1 minus P2. That's equal to C squared. If this is P2, this is your C square. Okay, this is the nothing but the this P1 minus P2. Sorry, this is C3 square. Okay. I think I call it C. Okay, here C only. Now this is your C square. This is true for every equation like P2 minus P3. All of them is also satisfied. I write it in terms of their distance parameters. Then please note we have some multiplication of terms. Okay, maybe let's write it here like P1 transpose P1, P1 transpose P2 minus P2 transpose P1 and plus P2 transpose P2. Now these are, I write it, these are nothing but P1 square, P2 square, okay, and these are given like, since their distance are S1 and S2, they are nothing but this last equation I'm talking about in the slides. That is equal to your S1 square, S2 square, and minus 2 S1, S2 cosine gamma is equal to C square. Okay, therefore I have three equations like this. Now I'm coming step by step. Note that I can define some auxiliary variables. There's a little trick here. I know the length. There is an unknown length S1 here. There is an unknown length S2 here. I simply divide S1 to S2. I gave it S1 to S2 is 1 over U, okay? I just obtain this result, and these auxiliary variables are make these equations. I get rid of one of the equations, one of the variables, and there will be three equations for S1 square, and all of them are in terms of only U and V. Okay, therefore only U and V, three equations. If you take two of the equations and get rid of the V, okay, then you will have a third equation just as nothing but as a function of V only, okay? Therefore, I just equate them to each other. I take U and write it in terms of V, and then I insert that U into the last equation. I obtain nothing but an equation of V, and also everything is known to me at that point. Please note this cosine alpha, cosine gamma is obtained through these vectors. These red vectors are helping me to find the angles, okay? Therefore, I know A, B, C, I know the angles, and I just obtained the result. At the end, you have like A4, A3, A2, A1. These are nothing, A0, they are nothing but scalars. a fourth order polynomial, and if you solve it, you will obtain u first, then v, and then you obtain the whole thing at that point. But unfortunately, fourth order, there are four solutions. You have to utilize one other. Point here, a P4, so that if you solve them, you will see that the unknown rotation and translation in between should be obtained for all the cases. There will be a common solution. Okay, the common solution with the fourth extra point, there will be four such problems with three points, and the common rotation translation for all these solutions is the solution that you are looking. What do we obtain? We obtain P1, we obtain S1, S2, we obtain P1, P2. Note that then maybe you have to find between two 3D worlds, okay? You have to find a simple rotation and translation, okay? Note that this is known, okay? This is P1, P2, P3. This is the model coordinate systems in 3D, and you will just simply solve for rotation and translation easily by just making a linear relation, okay? That is the part that we have seen about pose estimation. Now I'm gonna stop here. In the next lecture, I'm gonna talk about stereo imaging.